Okay, here we go. We're just doing the last page of the BC number one packet, 10.4. So we did everything else except for the last page. This has been a good packet review of a lot of good new BC stuff this year. So the last thing is Euler's method. Now, Euler's method is just a repeated tangent line approximation. You guys had to do tangent line approximations last year. I got paint on myself, by the way. I was painting. Tangent line approximation, or they call it, sometimes they call it a local linear approximation. And so you got to use a tangent line. So you need two things. You need a point and a slope. The derivative dy dx or y prime is going to be your slope. And then when we write the equation of a tangent line, it's, we usually use point slope form y minus y1 equals m times x minus x1. Now what we're using is the slope right here, y prime. We're using some previously known point, which at first will be the point of tangency. So I call this like x old and y old. And we're going to use these to find, now we're going to go to a specific x further down. And so that's the new x. And we're going to use that to find a new y. Now this right here, we often refer to as delta x. It's a change in x. And it usually is constant. So from this tangent line equation, the way that we usually use it, just kind of looking at it a little differently, the new y is going to equal the old y, because we're going to move it over to the other side, plus the slope, the derivative, y prime, times delta x. So you can use this to do this table thing that we did. Now, you probably only have to do this a couple times on the whole AP test, and each time you do, it's probably gonna be like a couple steps. So it might be worth it just to write a tangent line, get a new value, use that new xy value to write a new tangent line to get a new value. And, if you had to do it like 5 times in a row, then yeah, that's a lot of work. But if you can do it a bunch of times, maybe I'll ask you to do a bunch of times here, you could use this kind of table to do the same work, but to kind of just organize it. And we are using this idea right here. So, so it's going to be y new equals y new equals y old plus y prime times delta x. So it's not just enough to remember what goes in the columns, but also how they're related. So let's see if we can try that together. The solution of the differential equation contains a point. So it's your xy using Euler's method with the delta x of negative 0.3 to approximate y when x equals 2.7. Now, this is one step. So it is very possible that we could just be like, you know what? This is really the same thing we did last year. It's one step. I know it's one step because we're starting at x equals 3, and we're going backwards negative 0.3 each step. Well, one step gets you to 2.7. So this is really just one step. So you could say, okay, well, let's just write the equation of the tangent line. Now, you do need to find the slope, dy dx at 3, negative 2, and you have this equation. So you plug those in, and you get negative 9 over negative 2 equals 9 halves. And so then y minus negative 2 equals positive 9 halves, x minus 3. And then if you want, you could, simplify this, 27 halves minus 2. And so then what we're going to do is we're going to use this tangent line to approximate 2.7. And so we'll plug 2.7 in for x. And this is negative 31 halves. And 2 goes into this, 0.9. So we get 8.1 minus 15.5. And y 2.7 is approximately, this is approximation technique, negative 7.4, which is clearly wrong. So what did I do wrong? Let's see. Oh, right here I said that 2 goes to 2.7.9. That's actually 1.35. So this is going to be 9 times 1.35. 45, carry the 4, 27, 31, carry the 3 to 9 is 12. So this is 12.15. And then I'm subtracting 15.5 from it. So that's going to be what? Negative 3.35. Otherwise, you could use the table. It'd be a very quick table. You would just say, all right, well, let's make our table. We have our x, we have our y column, we have our y prime, we have our delta x. We're starting at 3, negative 2. We want to get down to 2.7. So our delta x is negative 0.3 each time. You can go backwards. That just means you're going to the left of the point of tangency, right? And then you can say, okay, well, the derivative is you plug 3 and negative 2 into there and you get 9/2 or 4.5. And then you say, well, the new y is the old y plus y prime times delta x. And after you figured it out, you would get negative 3.35. I mean, you probably want to do the work. You do 0.3 times 4.5. 3 times 5 is 15. Carry the 1 to 12 is 13. So that's going to be negative 1.35. Subtract, and you're going to subtract that from 2, which is going to give you negative 3.35. So same thing. All right. Why don't you guys try 23? Pause the video, try 23. Really, it's the only other Euler's method, I think, on this worksheet. So be good for you to try one. So go ahead, pause it, try it. All right. So either using the table, if you remember how to do the table, we're starting at 3, negative 2. And to create the table, you really you're not going to memorize this, right? I guarantee you're going to screw it up if you try and memorize it. I mean, you don't use it enough. So always go back to the setting up a tangent line equation, and from there trying to figure out what the table should be and what the relationships of things are. Now, we're trying to approximate 3.2. It doesn't, usually they say how many steps, so I guess we just assume it's one step, which isn't really much of Euler's method, but you plug these into y prime, and you'd get, let's see, 3, you get 5 over negative 4, you get negative 5/4, and that, and then delta x is 0.2. And so the new y would be the old y plus the derivative times delta x. So you got to figure out what 1.25 times 0.2 is. 10, carry the 1 to 4 is 5, 2, count back 1, 2, 3 decimal places. So it's 0.25, it's negative, it's going to be negative 2.25. Otherwise, you could be like, well, let's write the equation of a tangent line. And then you'd have to do it again if there's multiple steps. Okay, let's see. Why don't you guys try 24 and 26? Try 24 and 26 right now. So pause the video, try those out, and then I'll go over them. So 24 looks like some kind of time-dependent problem. It's a differential equation. They're giving you an initial condition, y1 equals 1, and they want you to find y2. So you could, this almost sounds like this seems like a good spot for fundamental theorem of calculus part 1. Problem is it has multiple variables in the derivative, so you really are going to have to separate the variables and solve the differential equation to do this problem. So we get the y over on the left-hand side by dividing it. You might leave the 2 on the right. It's up to you. I usually leave as much as possible on the right-hand side. And this might seem like a purely Calc AB problem. And so then you're going to integrate both sides. The left side's easy, natural log the absolute value of y. The right side, use substitution. No. T squared plus 2t. No, it's not inverse tangent. You guys realize what we need to do here? So this is throwing in one more Calc BC method. Partial fractions. So we're going to need to break that up. And the way we break it up is we factor the denominator, split them up. We got to figure out what those constants are. And then, so the way we do is we multiply through by the least common denominator, which is the original denominator, and you get 2 equals a t plus 2 plus b t. And then we use the cover up method, cover one up, eliminate it essentially to get the other one. So if we plug 0 in for t, we get 2 equals 2a, a equals 1. And then we plug negative 2 in for t, and we get 2 equals negative 2b, and b equals negative 1. So partial fractions, now, usually what happens with this is you usually get a lot of natural logs, but separate ones. So the 2 has already been taken care of. What I do when I rewrite these is I usually break them up, and I put the coefficient usually in front if it's something other than 1. And this one's going to be minus 1 over t plus 2 dt. So that's going to be natural log of t, absolute value t, minus natural log of the absolute value of t plus 2, plus c. We have to use the initial condition to find the c value. So I'm going to do that right now. The y value is 1 when t equals 1. Now, what happens is really pretty nice. A lot of stuff drops out, 0, 0. C equals natural log of 3. So then we rewrite it. Natural log of the absolute value of y equals natural log of the absolute value of t minus natural log of the absolute value of t plus 2 plus natural log of 3. So then we got to solve it. We're going to exponentiate both sides. Rules of exponents say that you can break this up into e natural log of the absolute value of t times e to the negative natural log of the absolute value of t plus 2 times e to the natural log of 3. So you can break it up into multiplication of the base, the same base. So that's going to be absolute value of t times, negative. You got to bring that inside before you cancel out the e in the natural log. So that's going to end up in the denominator, t plus 2, absolute value still, and then times a 3. So then got to get rid of the absolute value, so we got to do plus or minus. It did say that t is positive up here. That means that this is always positive, that's always positive. We can go ahead and get rid of those absolute values. If you plug 0 in, you're supposed to get 1 out. So that means we're going with the positive. And so this is your solution. And so now you can use this and plug 2 into it. And you get 3 times 2 over 2 plus 2 equals 6 over 4 equals 3 halves. So that was a differential equation, but involved partial fractions. All right, 26. Let f be a function that is everywhere differentiable. The table below provides information about f of x and its first, second, third derivatives for different values of x. Which of the following best approximates f2.2? Now, when you start looking at these answers, which you often should do, look at the answers. You look at these answers, and what do they make you think of? They make me think of series, right? Do you see that? Something to the first, to the second, to the third, divided by 2, divided by 6. Oh, that's a 3 factorial, 2 factorial, 1 factorial, 0 factorial, 2.2 to the first, 2.2 to the 0. So, anyways, you're seeing that sort of that stuff showing up on these. Now, what would be the best approximate for 2.2? Well, we'd want a series centered around a number that's closer to the value that we want to use for it. So I would say we should maybe go with 2 and do a Taylor polynomial centered at a equals 2, x equals 2. That seems like that would be the best if you're using it to get 2.2. So each term of a Taylor polynomial is the nth term is the nth derivative at the center, x minus a to the nth power over n factorial. Now for us, the x value is 2.2 and the a value is 2 since it's centered at 2. So that kind of rules a bunch of these out because we really should have a 0.2 to the nth power in each term. So that would make me think that we shouldn't use B, C, or E. So I think it should be A or D. So then the way you write your Taylor polynomial is you write the 0th derivative, which is the original function at the center 2 is 7.2 times 0.2 to the 0th power over 0 factorial. Well, that's just 1 plus the first derivative at the center 3.5, 0.2 to the first over 1 factorial plus the second derivative 1.75, 0.2 to the second power over 2 factorial plus 0.85, 0.2 to the third power over 3 factorial. So that would be a Taylor polynomial centered at 2, and that is exactly what D is. A just A looks like it's using all the values at 0, but then those numbers wouldn't make sense. If it was centered at 0, then it'd be 2.2 minus 0, and you would see 2.2s here. If you were going to center it at 0, which I guess is possible, right? And this one looks good as far as being centered at 0. This one's just wrong. And then this one looks like it's using all the values that we have here, but it has a 2.2 here. So it's using the values for x equals 2, which means it'd be centered at x equals 2, which means these would have to be 0.2s, right? Because you have to do x minus a. You have to do 2.2 minus the center, and these values are all coming from x equals 2. Anyways, that's it. You guys finish up the few problems we didn't do, and this has been a really good review assignment.